Hello and welcome to lesson 23, Practical
23.
Deep Learning for Coders Part 2.
Yep.
Okay. So I start with this notebook that this is not the right one. Sorry, everyone. Okay, so the first thing is what Ron actually mentioned last time about in last week's lesson, we talked about this, what was it again? We were doing the fashion mints classification, and it was the last model that they fit. And the FIDs were originally really low. And when we were looking at the notebook in the video, they weren't as low. They were like around 5. It was this Keras paper, yeah. And so that was something about a bug that he scaled the images, and because the Keras, because the FID score uses a model for the images, so the variance of essentially there was a scaling issue between what the range of the pixels were for one of those models. So one of them was only like,
wasn't the model -1 to 1, but he was using -0.5 to 0.5,
yeah.
what he was feeding in. And so that was the disconnect.
Yeah. So he had essentially cheated.
Yeah,
So
he said
these are
it
the
makes,
actual FIDs
yeah.
that we
He
saw
said
last time.
it makes all the images like sort of washed out and more like low contrast. So
Yeah.
they all
Yes.
look very similar to each other because of that.
Right.
Yeah.
Yep.
Yeah, so these were the appropriate FID, which we saw last time. Essentially that the Keras paper
Right.
didn't
We
really have
saw
much improvement, right?
we saw when
Compared to
Aaron
the
was
other
talking
ones.
about it, but when Aaron
Yeah.
was talking about what during the video, he was saying, "Oh, look how great this is," and it was only to the next one.
Yeah.
Oh, wait a minute.
Yeah.
Never mind.
Yeah, and you were way ahead of us on that, Ron. Pulling it up.
Yeah.
Well, like I
Yeah,
said, I
so it's
went
good we
ahead.
had Ron
Yeah.
last time to
Yes.
give everyone the spoiler.
Yeah, because I went ahead because I thought I was looking for a different bug I thought was in there, but that turned out to be my it turned to be that bug was existing between the keyboard and the chair, as they say.
Yeah, I think there was 2 bugs that he had. Yeah, so the scaling was in the data loaders code. Yes, okay, so then the next notebook is this one. There's several ones labeled 24, but it's actually this one, ImageNet Tiny.
Yeah, I noticed that too.
Okay.
There's several named ImageNet Tiny something too, right? There's like ImageNet Tiny.
Yes. So there are wide, wideish, 200, and then this one. Oh,
Those
this one
probably
has
come
an
up
A.
later.
This is the 200 epics. So don't
Oh,
probably
okay.
run this one.
Yeah.
Okay. And that's how he kind of got the
Yeah.
best performance, was with 200 epics.
The 200 is what pixel size? Is like 200 by 200 or what?
No,
The
200 epochs. Like,
epics.
Oh,
yeah.
I see.
Epoch, sorry. I
Yeah.
always say
Okay.
epics. Yeah, so this
I'm
tiny
never sure.
ImageNet. Yeah, some people say epochs. Let's see, I don't know if there's any examples. So this is a harder problem than the fashion or the digits. It's tiny ImageNet. They were describing it in the video as it was like 100 easy labels, and then they like added like 100 like hard labels. So there were things like cliff and cliff dwelling, which seem extremely difficult. So like here's an example of a water jug and a cat. And we are essentially we're changing our goal now. So in this lesson, we're switching from classification goal to super resolution. So imagine you have some low resolution images and you want to make a high resolution image. So our inputs are low resolution and the output is the high resolution image. So there's some data pre-processing. We have this probably not public anymore course link, but this still works to get to the zip. So thanks, I guess, Stanford for hosting this. That you can get all these images. Batch size, I believe 512. Here was a bunch of, essentially he did a bunch of string manipulation
Yeah.
to find all of the file paths. So we have this new class, tiny data set. I guess I can see.
Yeah, I don't remember all the details, but remember he talked about you have to have the length and the being able to get an index in a data set, right? Like those are the two requirements for those to work properly.
Definitely self-return. Yes, I think so. Let me see if I had any comments on the link, but not really. And then this is just essentially wildcard matching. And yeah, so this class, when you give it the, what did we give it? A path. And it returns for each index two things, the complete path to that file. And then this is the label. If we were doing a classification problem, this is the label. And these are some key index to, what did they call it? WordNet categories. Yep. So these are just labels for that. Okay, but then the validation one was different. I'm guessing because they didn't want to have the labels in the validation set. So that one, the validation set has this sort of structure. It just has a name, and then I believe the true label, he had to get it something else. Tiny validation. He's reading the annotation from somewhere else. And this was something interesting that he pointed out, a generator inside dictionary. So the way he has this here, this is a shortcut for creating a dictionary with a for loop. So this creates just a shortcut. I'm not in a Python environment, so I can't do the shift tab, but if you shift tab and predict it, it's like the third definition of dictionary. It had all the details about that shortcut. Okay, and then we have this transformations for our data set. Okay. All right. And so you can see that explicitly here where we have what we're returning, inputs, outputs are both being generated from one object here, I believe. Where we were setting up different from the classification task. All right, transformations. Just a little bit about reading and going from 3 channels and then scaling the 3 RGB channels and some normalization. Okay. And yeah, here's some of the examples. Water jug, cat. And these are some of the labels. Again, I don't, it's not printed here, but he did more string manipulation on this WordNet file, word text, split it by tabs, and then only kept the first. Some of these strings, WordNet strings, had multiple, basically a list of categories. So he just kept the first one. So it might have been like Egyptian cat, comma, fluffy Egyptian cat was the second label or something. You only keep one.
Mhm.
Okay. And then did some denormalizing so that it looks good for the human eye. It was an interesting discussion, not brought up at this point in the video, but later, about how validating these models is essentially just sometimes seeing if the pictures are visually appealing, which I thought was a very curious, like, motivation for building a model. I think we've talked about this before, maybe in this book club, about like, I'm personally more motivated by maybe like science or like scientific questions. So something like looking at a bunch of pictures to see if they look good. It's kind of the brain. I don't know. It's hard to imagine why someone would be motivated to do that.
Yeah, I hear you, but so much of the course has just been on images, right? So it's like
Yeah.
something that is, visually pleasing or not to our eyes. So I mean, it is
Yeah.
qualitative, but you know, I don't know. We're similar
And
enough that I think we can, you can make images that appeals to a lot of people, right? I guess
yeah. Yeah, I guess the
qualitatively say like, yeah, this
masses.
looks great.
Yeah. Yeah. So here are some of the examples. You could see that these labels are probably much harder than, like, is this a dress or a shirt or a shoe with no background, just isolated objects. Monarch, butterfly. Yeah, so this was the example. We had a cliff and then a cliff dwelling. So we're not expecting to have as high performance as we were seeing before. And here's our data loaders. Gonna get all the data loaders. We have a transformation for the training and validation, batch size, and then the number of workers you want. Okay. And so he's kind of walking through and treating it as like, okay, let's say we're starting from scratch. What do we know? What's something we can do really quickly to do this task? So again, we want to create a high resolution image from a low resolution image. So this basic model is an autoencoder. Okay, so we do have some augmentation, padding, random cropping, horizontal flip, and erasing. And we have to make sure that our transformations of this type, because, or not the random erasing, but things like padding, cropping, and flipping, we need to do them on both the X and the Y, right? Because if we expect, right, that the orientation of a low resolution and a high resolution image are the same. And for cropping, right, if we expect the same parts will be cropped and or padded. Right, you're not going to have a flipped low resolution image become unflipped through the network. We don't want it to learn that. We just want it to learn the resolution. But you can do random erasing only on the inputs to make the network have to learn how to interpolate things. Okay, and then this is the
Yeah, wasn't there
model.
something weird about like the random erasing happen at the same location in each image in a batch? As a
Yes, so
way to
that's
like
right here. We have batch transforms.
yeah, so
Yes.
that was like computationally efficient, even though that may not be the optimal way to do it.
Yeah, because you only have to run your random generator once per batch, which is less than once
Yeah.
per image.
Yeah.
Yeah. Yeah,
The only
so
other
I was
thing I remember
wondering if
from this
that,
section, just he talked about just not wanting to get crazy. I think just adding on to what you were saying earlier with your transformations, how you're augmenting the images, right? Because you could do
Yeah.
more damage than good.
Yeah. And I was wondering, because you had that spike, right, in your loss on that one. And
Yeah, it went
I
out of
don't know if
control.
that was a batch issue, but he was saying you can see things like that if you have one batch that was particularly over augmented or manipulated just
Yeah,
by chance, then you can see when it gets to that batch, it just sort of jumps. Um,
huh, that's interesting.
yeah, he mentioned that a couple of times. Okay. And then these are sort of the number of, I believe, filters or features. And then this is the model definition. So we have convolution into a residual block, average pooling, linear, etc. Okay, so these are some of the inputs, looks like X. And this is from one batch. Okay, yeah, so this batch doesn't really look like it had much augmentation, and he sort of went through and just, I think, went through different batches and found one. And they will have all the same. If a piece is missing, it'll be the same across all of these pictures. Okay, and then this was the summary of this model. And so he mentioned here that if we look in this megaflops column, because let's see, we're going from 64 by 64. And we are increasing the features, but we are doing decreasing this size. So these are all the same megaflops. I think he said that's like a good thing, but I don't really remember why he said that.
I vaguely remember the M flops. Is that floating point operations?
Yes.
Okay.
Yeah. So essentially, yeah, we kind of have the same number of operations, just in
Yeah.
different shapes.
Got it.
Okay. All right, then he used his little learning rate finder. We have the metrics. And here, because we're doing image to image, we are doing, wait. Oh, wait, why does it say accuracy? Oh, wait, maybe, was this a classification? No. Wait, but we have cross entropy here.
Yeah, I think he did start out with classification first.
Okay. Then I'm speaking in the wrong part of this. And yeah, 60% classification. Okay, I think I got ahead of myself. I'm
Yeah, that was
sorry.
classification because he's going to use that later. But
I didn't study my notes. Okay, yeah, so 24 is classification, and then notebook 25 is super resolution.
yeah,
I apologize for all of my comments. Are out of order. Okay. So 60%.
yeah,
All right. But he said it took a while and it's on the verge of overfitting.
right. Because the training was like 91% or something. Yeah,
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 91%
huge
on trading.
disconnect between
Yeah.
the training and validation.
And we looked at this plot from Papers with Code. Okay, this is, we're a couple years ahead. And the video was in 2022. So he was looking at this and looking here, extra training data. Right, so we're not using extra training data. We're not using, which sometimes can just mean using a pre-trained model, I think, right? Because a pre-trained model
yeah.
would be using different data. So he was looking around at these different ones that had an X here and looking in this. Is it this one?
I think it's the one above it that doesn't have a paper anymore. There's 72%.
Oh, okay.
Yeah, it doesn't have the paper. The reason why the paper's not there because it changed the name.
Um,
I had to hunt it down. It's called like harnessing hard mixed samples with decoupled regularizers. It was called something else during the when he was looking at it.
Okay.
It
And in the
was called
paper, a lot
decoupled
of their
mix up. Yeah, it was called decoupled mix up at that point,
decoupled mix-up.
but now it's changed.
This one?
Yeah, yeah. So you click that and you'll see that well, I guess that's not the archive, but on the archive it shows that it's version 1, then there's like a version 2, then a version 3 in October. Yeah. So for some reason they changed the name.
Oops.
Don't know why.
Probably the journal told them they need a new title.
Yeah.
I mean, we looked at this table a lot. So he was looking at, let me get rid of this. Need to get rid of this Adobe extension thing. All right, so he was looking over here and wanted to essentially, I think, prove to himself that he could get similar performance.
Mm-hmm.
And so we kept going on the notebooks. And so, yes, this was not an autoencoder. I apologize, people. Then we have this deeper model. Yeah, so what happened was he was like, okay, instead of having one residual block, we're going to have multiple residual blocks. So this line here is number of residual blocks. So we have 3, then 2, then 2, 1, and 1. So here in the layers, now we can see it's not using this res block. It's using now this wrapper res underscore blocks.
Right.
Okay, and adding multiple. So yeah, this was yeah. Did anyone have any recall like the intuition that he shared about increasing that?
No, he just decided he'd rather than go down more stages. He just said, "We'll just do several res blocks in a row at each number of features, and then go down." Right? I guess that makes sense because then it's yeah.
Yeah. Oh, and here now is an example where the batch, you can see they all have this same like padding at the top.
Yeah.
Here we have like a stork or something, a mollusk fish. Okay, but now we have more.
Mega flops.
Yeah, this is about twice. This number was about twice as the other model. Okay. Metrics. So now we have 2% better and less overfitting.
Yeah.
With making the model deeper by adding the res block. Okay. All right. Now here, this was a fun section for me actually. Here, now as it says, more augmentation. So he's thinking, okay, let's add more augmentation. And specifically, we're going to do this trivial augmentation. Okay, here is the paper. Oh my gosh, no, I don't want to annotate. I want to click this PDF. Zoom has like this little, you guys probably can't see it, this little pencil here that says annotate, right where that PDF button was.
No, I didn't see it.
Okay, and there's this one algorithm, it's really great. And it says,
Oh yeah, this is funny, yeah.
This augmentation strategy is just you provide some different augmentation strategies in the set A and you just randomly sample one. and apply that one. And A might have, yeah, like some value or extra parameter that it needs to do that augmentation strategy. So yeah, you just randomly choose an augmentation. And this algorithm, yeah, is for the augmentation of an image, but I believe in the notebook, let's check. Is it still on the batches? But that's what this is, and he doesn't implement it himself. He just uses this trivial augment wide, I believe, from PyTorch.
Yeah, it was built into PyTorch, I think.
And then you have to do this whole transformation from an array to a Python image library, Python image library. Do a different type of object in Python, essentially. So that's just what this sort of is. So he's using the Python image library to open, then doing the augmentation, then making it back to a tensor after the augmentation. And again, it's just because these functions don't work on that. Okay, so more augmentation, data loaders. All right. And here okay, so yeah, it looks like he did image wide transformations or augmentations and transformations, right? So each of these images in this batch have different shearing, erasing, padding, cropping, etc. All right, this one. Yeah, so then he got to 60, 4.9. He looked in that paper that we just found, decoupled mix, and said, hey, my results are like basically as good as this. So I'm gonna stop. And I was like, okay, sounds good. So yeah, I guess the point of this notebook is just an introduction to the new data, tiny images, and the res block stacking and trivial augmentation. Okay. Oh, and then yeah, I do have one. There was one small discussion on, right, we're doing these small images, right, meaning fewer pixels, meaning you can overfit easier because just the dimension is smaller. So that's why we are doing a lot of data augmentation. That's probably why one of his strategies was more augmentation. Okay. Yes, and does not recommend doing batch-wise trivial augment. And then yes, that 200 notebook helped a lot. It looks like I didn't talk about this. So there is this pre-activation ResNet. Oh, I downloaded the paper. Gave myself a note. Is this it? Yes, this identity mappings. Does anyone remember this? So
Yeah.
there was yeah. Oh yeah, so this is what we've been using. So we have some input X, and in the ResNet, we add it, right, we add the identity to some transformation here on the right, and then we do a ReLU. So this ReLU here, because we're adding things, it usually, I guess, notice it usually doesn't actually do any changes. And so they moved this ReLU essentially over here. And then another weight and then added. So that there's more, I guess, ability here. That's what I remembered them saying, was that having it in this order, addition, then ReLU, was most of the time not changing. So the difference between addition and ReLU, I guess, would most of the time be 0. And then by restructuring it in this way, there's more diversity happening, I suppose. Did anyone else have another interpretation of that?
I didn't get too deep with this. I mean, I
Yeah.
along, but yeah, I just didn't
Yeah.
really, I glossed it over.
Yeah, that's what I thought. I think they were saying. But I might be again misconstruing. Okay.
Yeah, that thing you highlighted was the main point, that there was like a
Yes,
true, it was
a true
possible for the
identity
model
graph.
to pass through the inputs directly through the outputs, at least through the ResNet block. Whereas before it couldn't, because it was having that ReLU squashing it. So that for deeper models, that's more important. You
Okay.
don't lose things as it goes through.
Okay. So yeah, let's clean that up a bit. So yeah, so here then what we're saying, the one of why we think a res block helps, yeah, is because we have the identity from here moving forward. But when we have this ReLU, like Ron was saying, it can this XL and then this XL plus 1 probably aren't that similar. Now we move that on the right so that we have a true identity.
Yeah.
We want XL and XL plus 1 to be similar and maybe just perturb some by this addition.
I mean, in principle, they could be exactly the same, right? If that weight was 0.
Yeah, if
on the
all of these
right.
weights are 0. Mhm.
But on the left, they wouldn't be 0 because that ReLU would take out all the negatives, right?
Yep, exactly. Okay, great.
But I guess,
Um,
like Jeremy was saying, he has said a lot of these things, and the proof is in the, in the success that you get with it, right?
Yeah.
If it didn't work as well, we'd probably think of some story why passing through directly was bad or something, right?
Yeah, yeah.
The stories we tell ourselves are what they did.
Mhm.
The other ones, the results.
Yeah, and then I guess we can look at this point he asked his helpers, like, do you have any other ideas? Anyway, I think it was Tanishq asked about dropout and Jeremy just said dropout makes everything worse. So this is the 200 notebook he ran for 200 epochs. So again, do not recommend running this at home. And he gained a few percentages. 67.5. And the motivation for that was because here in this paper, I think they did like 500 epochs. So he wanted to do something on a similar magnitude. All right. Okay, now I can go back to my super resolution spiel. This is what happens when the videos cover so much and just
I know.
yeah,
Next week's a 2-hour video. It's like, ugh.
get it all mixed up. Oh, sorry. I'll watch it, so we're not bold. Okay. So yeah, so then in notebook 25, now we are doing this for resolution. So we have these images. Again, now this is where my statement before about applying the padding, cropping, and flipping should be done the same to both the input, the low resolution, and the output, the high resolution. So this is like kind of like his line there. Okay. And this is all data processing. And then yes, but you can do just on the X random erasing to give your model even more of a challenge to not only increase the resolution, but interpolate missing pieces of your picture. Okay, here's some images with random erasing, and then again in the Y. Right, so let's just look here, what I was saying. Any padding, shifting, or cropping have to be the same from this input batch to its label, which is now a high resolution image. But the random erasing, we can do just on the input X. And hopefully it will learn to make the fuzzy parts more clear and interpolate what's missing here. Okay, so now we're here where I was saying the autoencoder might be a place to start if you don't know any, if you're just playing around using what we've learned so far in the course. Doing the autoencoder, I have the up block. Okay. And then we have some res blocks, res block, up block. Yes, so here he scaled down the inputs are 32 bits. And yeah, he basically said this autoencoder is a dumb thing. So we probably don't need to spend a lot of time here. But yeah, so this is how I noticed last time I was saying the wrong thing. Our loss now is MSE. Right, we're comparing image to image. So essentially, I guess pixel-wise MSE. So this is some number. We don't really have comparison until we build another model to see if this. Okay, but we can look at what it learned. Okay, so here's the inputs. And here's what the autoencoder does. It basically just gives you a very extremely smooth version of your low resolution image. You wash out all of the details. So you can't see anything anymore. Yeah, I guess I'm still not really sure why he even did that. Like an autoencoder. I don't know. Just a practice, I guess. Okay, but or maybe just to make the connection to the UNet paper about shape. So this is the first UNet paper. So if we think about the autoencoder, right, it kind of also has a U shape, right? We have the downsampling, upsampling. But what's happening is it's sort of forgetting where it started when we have such a low resolution. So in this paper, PDF, all right. Like this. This is the original paper. It was on medical imaging, and Jeremy mentioned he used to work on medical imaging. And the figure we want to look at is here. So, right, this shape, if we ignore the middle, I mean, you could maybe think of this as like an autoencoder. You're going down in size and then going back up. So downsampling, upsampling. Along the U, that I mean, basically is the same idea. We have some convolution layers, max pooling in red, convolution, max pooling to go down, and then convolution and upsampling to go up. To help our model not sort of forget, right, what the input image is. Not sure if you can see this, but
Yeah, pretty good.
these dashed rectangles follow this gray arrow and get copied, concatenated in the upsampling side. So essentially what we're saying is over here, when we get back to this dimension, which is like 392 by 392, it should be similar to what we had over here, because this is very close to what we input. So the features that we input, right, like the general shape of that kid's head or the guacamole bowl, those should still be there. We shouldn't forget them when we get over here. So this is to help the model remember faster, I suppose, by concatenating over here.
Yeah, I
So
mean,
they
is the
do it
idea,
in multiple places.
did you get the impression that the idea was kind of so that the model would know where stuff goes? I mean, would know like the basic
Yeah.
layout of the land. I mean, you know, like this part it should be like
Yeah.
a head. Well, otherwise it really is just kind of like lost all that information. It seems like when it's,
Right.
you know, it goes down to like a very small, well, I don't forget how small it goes. Let's say it's a 4x4 image with like a whole bunch of, um, a whole bunch of features, but it's hard to figure out where those things actually go now, right? In the XY.
Yeah.
So maybe that's what that does, I think. I don't know. I'm just speculating.
No,
have
I think that's a good I mean, that's kind of my intuition as well. Like
Okay. All right.
if you have fine scale features that you know from the input, when you go down, right, there's only so many ways you can compress fine scale things, like local things. So yeah, this is kind of like saying, oh, don't forget about these local things that we input. Yeah. And so yeah, in this, sometimes if the dimensions on the downsampling like don't match. So in this paper, the dimensions on the down path are a little bit bigger than the up path, so they actually do some cropping. And they just take the center, I guess is what is implied by these boxes. They crop from the center and then they concatenate here. So yeah, that's the unit architecture and my interpretation of the intuition. I also did not read this paper, but if we look here, so yeah, I think what Ron is, you're right. I think when we did this one, we went all the way down to, actually, I'm not sure what we
I don't
went
know either.
down to. I can't really read that fast
Can't
enough.
tell from there either.
Yeah. Okay, so the UNet, then this is that entire UNet model.
I mean, it divides by 2 every time, right? Or every big block.
Yeah, so if you start with 32 and divide by 2 each time, yes. So yeah, stride 2 get you down. Yeah, so here is the down, and then, or sorry, let's look down here. For the down part of the U, right, we just apply our layer transformation. But then we just see here for the upsampling, we're adding back a previous some other layer from the other side. Here we're adding it back, so that was that gray arrow going across, and then this is just for the final layer. You're adding back the first one. Okay. And then he talks a little bit about initializing weights. Okay, and he says, okay, well, let me go back to that paper actually. He says, okay, well, a good starting place would be if I basically just copy this over here and I have my something really close to my input image being my output. And so he's going to zero out some of the weights to start the model there. So to start the model, to have this side be really close to what the input was. And yeah, I should note in the code we did adding. So we added the white and blue together rather than concatenating. Right, so yeah, so we're adding and not concatenating. So yeah, so we can zero out some weights. We're not zeroing out, I think, all of the weights, only these indices. So the ones at the end and the ones at the beginning, maybe. And I think then we entered this discussion about why people are scared to initialize at 0 and if it should be a really small constant. And Jeremy just basically said it's just tradition that gets passed down from PhD advisors to PhD students to not initialize at 0. But I think something that helps here is I think I'm understanding that he isn't zeroing out everything. So I think that's also like helping. Okay, and then we learn the model. Or no, we're doing the learning rate finder here. We have the model zeroing bits and epochs. Okay, so our previous autoencoder MSE was 0.2. And now we get something really small. Much smaller, 0.073. These are, again, the inputs. And now the outputs. So yeah, so it remembers, right, those sort of outlines of the pieces in the image. And yeah, they at least look similar. It just essentially looks like it, you know, a fuzzy version of the low resolution images.
Fuzzy but smoothed, I guess, instead of
Yeah.
fuzzy.
Yeah, it's smooth, yeah. But of course, and this was his favorite one to pick out, our koala doesn't have an eye. Child doesn't have a white of his eye. And I don't think we ever found out what this was a picture of during the video. There's some pill bottles, a bus, fan. These are like, I think those inflatable punching bags. Candy store. Okay, I think these are the true ones. Yeah. Okay, so we got a much lower loss, but then this is where that whole discussion about,
Right.
well, does it look like a good image? Not really. It looks like a computer made it. So if we want something that a little bit better, let's make some changes. So the first change we make is on the loss function. So before we were using MSE, and I'm sure y'all are aware, like MSE doing the squared is really contributing to this smoothing that we see. It happens a lot. You use Gaussian kernels, you get really smooth you do kernel density estimation. Basically anything that you use Gaussian functions for will give you very smooth, even like interpolation, spatial interpolation or Gaussian processes. I don't know if y'all use that. So if we want to make it a little bit sharper in features, maybe we need to change the loss. So he introduces this idea of perceptual loss. And let me look here, my notes. What I need to, okay, Ronenberger, we need to look at. Oh wait, no, that was the unit thing, perceptual loss. So this is in the realm of our FID. Okay. In the sense that we're using another model to inform our loss. So this was a kind of an interesting idea where the perceptual loss says, let's look at a layer of our current model that we're fitting compared to a layer, I guess, of the same dimension from a pre-trained model. So for example, our classification model. And let's see how far those are from each other. So this loss is a function of another pre-trained, in this case, classification model. And I have some dots here. This part, we can look at the code. There's some gradient tracking also, so it's kind of. Just so we are loading in our classification model. Then we are, let's see, looking at the shape. So we're going to have this shape. We have our, okay, we're just getting these for labeling down here. It's pictures. These were the predictions. Okay. So some of them are not right. Like this is a band, clearly not a coral reef. This is not binoculars probably. And I really don't know what this is, but it got labeled as barbershop.
Some things aren't wrong.
Yeah, some things are not wrong. Punching bag, refrigerator, koala, mush. Like most, I would say, what, like 80% of these seem right?
60%. Remember,
60.
wasn't it?
All right.
Wasn't
Oh,
it?
yeah, it was 65%. Yeah. All right.
Aaron's shaking his head.
Okay, so this was how we essentially deleted all of the layers. Right, so we just want this model to end at the feature that we're going to use in the loss. So we're deleting all of the layers after that. And this took me a little bit to understand why he kept 4 here, but then I realized like, okay, well, when he deletes the first one, then the one in the 4 position will be a different one. So it's just gonna keep deleting that position. Okay. Okay. And so here we have this 1024, which sort of match this. Right, so here if we have 200 predicted labels, or 200. Okay, so computing the loss now, we have 2 things, MSE, and this is the perceptual loss. So we take our classification model on our target and get that feature. But and this is with no gradient because it's on the target. But here, this is the part where I was like, we have the model on the inputs. So is it changing the weights for both models?
Yeah, wait, why does he want that? I didn't notice that, but you're right. It seems like he wouldn't want to change that model at all, just leave it torsional graph for both. That's
Yeah.
interesting.
Yeah, I didn't. Maybe that can be like homework for me.
Or should it be frozen? I don't know. I guess you do want the weights to go through to the input.
Yeah.
No, you do want the weights to go through there. You want the derivatives to go through there, flow through there back to the model because you want to get the actual model affected by the loss. So, but I worry that the C model will also now be affected by it, won't it? I don't know.
Yeah, I'm not sure either. But anyway, we have the classification on the target on the input. These were both have this 1024. And then whenever you do these additive losses, like this has come up also with some other work I do, you kind of want them to be on the same scale. So he just kind of got this 10 by running it, I think, like 1 epoch, and then kind of looking at the ratio of the losses and then saying, okay, this one was 10 times this one. So let's just divide by 10 so that they're on the same scale. And then I don't remember the reference, but it came up later that there was like a magic number in another paper that was like 0.1 times. So maybe 10 is a good default.
Yeah.
Okay, and then here's our
think that through
zero
like real
weighting.
quick, like about like why why would we want to make that on a similar scale? I mean, isn't that kind of like when I think of like regularization, right? Where it's like, it's the bias variance trade-off.
Yeah, so I think it's because of the like derivatives. So the size of the gradient will depend on the magnitude of this, and if one overwhelms it, might only like move towards that minimum. I'm not sure.
Mm,
That's kind of my guess.
okay.
Have any thoughts, Ron?
I just figure it's like another hyperparameter you must have adjusted. But
Yeah. So my other work is actually not even deep learning, it's a Bayesian model, and we have but we have Bayesian regularization, feature regularization, and those tuning parameters we also have to tune to sort of be on the same scale as our like likelihood. Otherwise it like goes to one mode that doesn't really give us anything useful about our data inference. So that's kind of where my intuition is coming from in interpreting this. We have our learner rate finder, 20 epochs, perceptual loss. So now the loss function is different, so we can't compare these values to the 0.067. I suppose you could like just calculate the MSE by itself here, but because it might not be necessarily better, but we might have better results in terms of the human eye. Okay, so 0.3 then is our perceptual loss. Again, these are those same images. This is our input. This is our output. So we don't have any koala again, but now we kind of have a pupil on our child here.
a weird looking one, but yeah.
Yeah, it's kind of like on his face, or their face. And again, these are the true ones. He kind of says that he thinks there's better backgrounds now. There's more texture here in the leaves. Okay. This label still says perceptual loss, but this is the freezing and unfreezing trick, I believe. So let me just go to my notes for a second. So the next trick is then he says this is Fast AI's trick. He says it's cheating, but they call it unfreezing pre-trained networks. Okay, and he says this is cheating because remember in a perceptual loss, we're using this pre-trained network to calculate part of the loss. So he says it's cheating because the transformation is now being used. The weights are being both used in the model and in the loss. So how it works, I actually thought this was pretty clever. So you use the weights from the pre-trained model. So we have the classification model, right, which is sort of going down in dimension from an image to one label, right? So you use these weights from the pre-trained model as an initialization of your downsampling path. So hopefully, just give a catalyst to your new model saying like this other model must have already learned something. Okay, so maybe you can use a new model. Okay, and so the way he mentions doing this is first you do one epoch where you only have the gradient on one side. So I believe that you freeze the weights from the pre-trained model, and then you only do one gradient on the upsampling. Then you sort of have like a good guess of upsampling, then you update everything else. And I have this note here. This also reminds me of some like MCMC tricks, so Bayesian tricks, where we like, maybe we fit just least squares algorithm and then use that to initialize our Bayesian regression that time.
Yeah.
Because like in theory, you should be able to find the stationary distribution, but in practice, I'm not gonna wait for that.
In practice, you end up
Okay.
often dealing with multimodal distributions going into the
Yeah.
wrong mode. Yeah.
Yeah. Okay, so again, we're loading this pre-trained model. Okay, and then we turn off the gradient. And then we, okay, sorry. We load it and then we add it to our model as this is sort of the initializing. So we initialize, turn off the gradient, do one epoch. Okay, so with one epoch, 0.255. And then after the one epoch, you turn the gradients back on and you train as usual. And we got down to 0.198. So I think the other one is like 0.303 for the perceptual loss. These are both with perceptual loss. Okay, so we have the same images and yeah, I don't know. I mean, he goes through saying how he thinks this is a little bit improved. I think I didn't stare at it as long as him, but yeah. Yeah, we still never get this Wallace eyeball.
There's a hint, he said, I think, one, but yeah.
Yeah, there's like maybe the little fur changed color.
That's all we get.
But no. Maybe the child doesn't look, his eye doesn't look like a cartoon eye anymore. Okay. Now, we still want to get this eyeball on this koala, so let's another. Oh man, I'm talking forever. I'm sorry. This is the last thing. I wasn't watching the clock.
That I like how you said, we gotta get that eyeball on that koala,
Yeah.
that koala or else.
Yeah.
No one goes home until the
Yeah.
eyeball gets that koala.
Okay, but there's just this one last thing, and this is called cross convolution. So let me just look here. It's a residual block followed by a convolution. Yeah.
Maxwell.
Yeah. So cross cons. Yep. So we just have res block, then we have the convolution of the res block. Okay. I apologize, I went over time. This one gets to 0.189. And look, yeah, I got an eyeball. Great. Well, thanks for discussing with me today.
Yeah, no,
And
it was good. I mean, it's a long, that's the problem with these things. They're getting longer and more deep, seemingly pretty dense too. Like the next